Hello and welcome to this chemistry lecture series. In this video we're going to take a look at chapter 16 section 3, which is going to cover the mechanism for the nucleophilic substitution reaction that we saw in section 2. This is a reaction of halogenoalkanes where the halogen gets replaced by either hydroxide or hydroxyl group if we're using an alkali, a nitrile group, or C-triple-bond-N if we're using cyanide ions, or an amine group, NH2, if we're using ammonia. So let's look at how these reactions that we already covered happen. So the mechanism of the reaction. Nucleophilic substitution reactions, as we discussed earlier, happen because of the polarity of the carbon-halogen bond. Whenever we have a bond between a carbon and a halogen, like chlorine, iodine, fluorine, the carbon is going to be partially positive while the halogen becomes partially negative. And that's because of the difference in electronegativity. Halogens are a lot more electronegative than carbon is, making that carbon partially positive. Now, the carbon-halogen bond in halogenoalkanes, leaving that carbon partially positive means that that carbon is going to be a perfect site for nucleophilic attack, for a nucleophile to come in and attack that carbon. Remember from chapter 14 that a nucleophile is a compound that has a lone pair of electrons and either a partial or full negative charge. So whenever we have a nucleophile, we're going to symbolize a nucleophile usually by writing Nu. Oops, let me make that a little smaller. Usually by writing Nu with a lone pair of electrons, because nucleophiles have to have lone pairs of electrons, and a negative charge. This Nu could represent the hydroxide ion if we're using an alkali, the cyanide ion if we're using potassium cyanide, or even ammonia if we're using ammonia as a reactant. What's going to happen here is that because the carbon-hydrogen or halogen bond is polar, that nucleophile, and again nucleo meaning positive, so this is a positive loving molecule or ion, is going to attack our carbon, which is partially positive. So it's going to use its lone pair of electrons to attack that carbon and substitute the halogen. Now, there are two different ways in which this can happen. The mechanism for a nucleophilic substitution in a halogenoalkane can actually happen in two different mechanisms. The first is SN2, which stands for substitution nucleophilic secondary, or SN1, which stands for substitution nucleophilic first order. So second order, first order, should I say. So for SN2 and SN1, the mechanism that's possible here in two ways is going to be dependent on the type of halogenoalkane that we have. Not on the halogen. All halogens, chlorine, bromine, iodine, fluorine, can undergo both types of mechanisms, but the type of halogenoalkane, meaning whether that halogenoalkane is primary, secondary, or tertiary. And we discussed primary, secondary, and tertiary halogenoalkanes in section 1. A primary halogenoalkane, is going to be, or is going to undergo SN2 mechanism. And we'll get into the difference between SN1 and SN2 in the next couple slides. But first, I want to point out that what dictates what of the mechanisms the different halogenoalkanes undergo is whether they're primary, secondary, or tertiary. So a primary halogenoalkane is going to undergo an SN2 mechanism. And just to remember, a primary halogenoalkane is going to be one, where the halogen is bonded to a carbon with only one other R group, one other carbon chain. Whereas a tertiary halogenoalkane, let me use a different color here, a tertiary halogenoalkane is going to undergo SN1 mechanism. So whether that halogenoalkane is secondary or tertiary, it will cause the mechanism change. The reaction itself doesn't change. We still get the substitution of the halogen for whatever the nucleophile is. But what changes is the way in which this happens. Just to remember, tertiary halogenoalkanes are going to be ones where the carbon that the halogen is bonded to is bonded to 3 different carbon chains, 3 different what we call alkyl groups sometimes. So depending on whether the halogenoalkane is primary or tertiary, we will get a different mechanism happening, either SN2 or SN1. We're not going to ever get a question regarding secondary halogenoalkanes, because secondary halogenoalkanes can undergo either mechanism, and so it's a little more advanced to figure out which mechanism they undergo. So anytime you're asked to draw the mechanism of a nucleophilic substitution reaction with a halogenoalkane, you will either be given a primary or a tertiary halogenoalkane. And depending on which one you're given, you will use a different mechanism. Both mechanisms will involve a nucleophile attacking the carbon, but how that happens changes. So let's get into these mechanisms. SN2 mechanisms are first. So let's look at SN2 mechanisms. The S in SN2 stands for substitution, the N for nucleophilic, and the 2 for second order. So again, the S stands for substitution, because it is the substitution reaction that happens here. The N stands for nucleophilic, because that is the mode of action. It uses a nucleophile to do the substitution reaction. And then the 2 stands for second order. And this is a vocabulary term, second order, that has to deal with the rate of the reaction. However, we do not look at orders, second order, first order, until we get to A-level chemistry. So right now, just know that the 2 means second order, but you don't need to know what second order means itself. All right? So the mechanism for an SN2 mechanism, for an SN2 substitution, consists of a single step. And this is very important here. This is going to consist of only one step, which can be confusing considering that the mechanism is SN2 with the number 2. Just remember that the mechanisms are a bit backwards from what you see on the name. A SN2 mechanism happens in a single step, in one step, whereas an SN1 mechanism happens in 2 steps. So they're the opposite of what you see. So the SN2 mechanism happens in a single step that is going to consist of what we call a transition state. Now, a transition state in chemistry, in mechanisms, because this is a vocab word that's specific to mechanisms, is a theoretical highest energy structure along a mechanism or a reaction pathway that usually consists of partial bonds. Now, what are partial bonds? Partial bonds are half broken or half formed bonds. So they're half bonds. Bonds that are either in the process of breaking or in the process of forming. So they're theoretical because they're not going to be part of an actual compound that is stable. They're going to be part of what we call a transition state, a theoretical representation of bonds being made and bonds being broken. This is not an intermediate. Intermediate is something else that we will see in the next mechanism. But I want to make sure that I point out a transition state is not the same thing as an intermediate. Because intermediates are stable. They are compounds that could work, that could actually exist, that we could gain information for. Whereas a transition state is completely theoretical and completely made up with partial bonds being half broken or half formed. So the mechanism for an SN2 mechanism, the mechanism for this nucleophilic substitution reaction, again, is going to happen with compounds or with halogenoalkanes that are primary. So if we look at this halogenoalkane right here, for example, this is a primary halogenoalkane because the bromine is bonded to a carbon that only has one other carbon bonded to it. So that makes this a primary halogenoalkane. Because it's a primary halogenoalkane reacting with a nucleophile, in this case our nucleophile being hydroxide ions, this is going to undergo SN2 mechanism. Because again, it's a primary halogenoalkane undergoing a nucleophilic substitution reaction. So how exactly does the SN2 mechanism work? How does it happen? During an SN2 mechanism, what is going to happen all in one step is that the halogen will leave the carbon at the exact same time that the nucleophile is being added. Remember, a substitution reaction can be seen because the halogen in the halogenoalkane is going to be substituted by the nucleophile, in this case, the hydroxide ion. So we can see how from the reactant to the product, we have that bromine being replaced by the OH. In SN2, that happens all at once. That's going to happen all in one step. That's why SN2 reactions are going to happen in a single step. So if we look at this, what happens is that the nucleophile, which again has a lone pair of electrons, a negative charge, is going to attack. Those electrons are going to be used to bond to the carbon. This happens because this negative nucleophile with its lone pair of electrons and its negative charge sees a partial positive carbon. It's like, how you doing? It wants to go to it. It wants to bond to it. It's attracted to the positive charge on the carbon. At the same time that happens, at the same time that the hydroxide forms a bond to the carbon, well, the carbon would have 5 bonds if that bond were to form. So it needs to break off one of its bonds. So at the same time as the hydroxide, in this case the nucleophile, is attacking the positive carbon, the carbon-halogen bond gets broken heterolytically. So at the same time that the hydroxide attacks, the carbon-halogen bond, the carbon-bromine bond in this particular example, is going to be broken heterolytically. So it'll be broken heterolytically so that both the electrons in the carbon-halogen bond that is breaking heterolytically go to the bromine. So that's where this transition state happens. This transition state is not actually a step. It is us visualizing what is going on. This is all happening in one step, and that one step is going from the halogenoalkane to, in this case, the alcohol. That's one step. The transition state shown here in the middle is just the process, the theoretical visualization of what is currently happening. When this happens, the hydroxide, the nucleophile, is forming a bond to the carbon. So that is a half-formed bond. And that's why we see it in dashed lines. And then the carbon-bromine bond, which was already there, is now breaking. at the same time that that other bond is being formed. So this is a half broken bond. So this is all happening at once. So the transition state is just us visualizing that process. What ends up happening is that the hydroxide gets attached to the carbon and forms this alcohol, which we saw in the earlier section. And then the bromine, which broke off heterolytically and took both electrons, is going to create our Br minus ion, our bromide, ion. And you might notice that that bromide has a negative charge because of the electrons that it picked up from breaking the bond. So that's the SN2 mechanism. It happens all at once. The transition state shows the half-formed hydroxide to carbon bond and the half-broken carbon to bromine bond. So it's all happening all at once in one mechanism step. Now, what about SN1? Well, in SN1, we are going to have a two-step mechanism. So SN1, again, the wording is very similar to the before, because S still means substitution, because these are still substitution reactions. These are two mechanisms for the same reaction. S is still substitution. N is nucleophilic, because again, it's a nucleophilic substitution reaction. Same reaction, two mechanisms. And what changes is the fact that this is a first order reaction. That's where the one comes in. First order, again, is a rates vocabulary term. It's something we use that tells us a lot about the rate of the reaction. But it's something that we are going to visit in A-level chemistry, not right now. So it is something that you do need to know, that the one means first order, but you do not need to know exactly what first order means. Now, first order reactions are two-step reactions. So unlike SN2, which was a one-step, SN1 reactions happen in a two-step mechanism, meaning that they are going to happen one thing at a time. With these SN1 reactions, we get what we call an intermediate. The intermediate is the molecule formed between the two steps. It is not hypothetical. It is not a theoretical representation like it was with the transition state. It is a molecule that is stable enough to exist, even for a short time, and show evidence of that molecule existing. So in the two steps of the SN1 mechanism, we're essentially having the exact same thing that happened in the SN2 mechanism happen, but we split up the two steps. So instead of the nucleophile attacking and the bromine or the halogen leaving or breaking off at the same time, we have those two steps happen separately. So first, in nucleophilic, in SN1, in the nucleophilic substitution mechanism, SN1, we are going to first have our tertiary halogenoalkane. And again, this is tertiary. Why? Because, this is tertiary because our bromine is bonded to a carbon, which has 1, 2, 3 other carbons bonded to it. So that makes this halogenoalkane a tertiary halogenoalkane. When we have a tertiary halogenoalkane, the nucleophilic substitution reaction will happen in two separate steps. They will happen in SN1. So what happens first? The first step of an SN1 reaction, the first step of the SN1 mechanism, is for the carbon-bromine bond to break. That happened along with the nucleophilic attack in SN2. In SN1, the first thing that happens very slowly, is that the carbon-halogen bond, in this case again bromine is the halogen we have, is going to break heterolytically. What that does is that when this bond breaks, it creates a negative bromide ion, which is one of the products of our reaction, and a tertiary halogenoalkane. Because that carbon loses a bond, it is now positively charged, meaning that we now have a tertiary halogenoalkane. So we go from a tertiary carbocation. So we go from a tertiary halogenoalkane to a tertiary carbocation. So this tertiary carbocation is now made by the first step. Well, in the second step is when the nucleophile comes in. The nucleophile, which could be hydroxide in this case, it could be ammonia, which is a partially negative nitrogen, it could be cyanide with a negative charge, but the negative nucleophile that's floating around, in this case with an alkali, will use its lone pair of electrons to attack the carbon. That nucleophile sees a positive charge on the carbocation, and it's like, how you doing? And it uses its lone pair of electrons to attack the carbon and form a bond to it. So that bond is created to make our alcohol as a product in the second step. So the products are the same because these are the same reactions. We still get that alcohol in this case because the nucleophile is a hydroxide. We still get that halogen halide ion, which is the bromide ion. It's just how it happens that changes. With a tertiary halogenoalkane, it happens through the SN1 mechanism, which has two individual steps. Whereas with a primary halogenoalkane, it will happen with an SN2 mechanism in one step. SN2 mechanisms have a transition state, which is a hypothetical representation of the progress, not an actual molecule. Whereas an SN1 mechanism, which is a two-step mechanism, will happen in two steps and form an intermediate. The intermediate in this case is going to be our carbocation, because that's the compound that is made during this first step of the reaction. So this carbocation right here is our intermediate. Again, why is it intermediate? Because it is the organic molecule. Yes, I know the bromide is also made during the first step, but notice how that organic compound, the carbocation, is created by the first step and used in the second. Bromide is not an intermediate, it is a product. So those are the two mechanisms for nucleophilic substitution reactions. Now, let's talk about why these are different. So why does a primary halogenoalkane undergo SN2 mechanisms while a tertiary halogenoalkane undergoes an SN1 mechanism? And the answer lies in this intermediate right here, the carbocation. Notice how SN1 mechanisms create carbocations, but SN2 mechanisms skip it. There is no carbocation present because the nucleophilic attack, the attachment of the nucleophile, happens at the same time as a carbon-halogen bond breaking. We do not create a carbocation during this SN2 mechanism. And that's where the key difference lies between these two reactions. Carbocation stability and nucleophilic substitution are connected. We spoke about this earlier in the chapters. I think it was chapter 14 maybe that we spoke about this, or maybe chapter 15. But tertiary carbocations, which are formed by tertiary halogenoalkanes, are more stable than primary carbocations. Why is that the case? Carbocations formed during the mechanisms are going to be subject to what we call the positive inductive effect. The positive inductive effect in the carbocation is the release of electrons from organic groups, like an alkyl group, like a carbon, towards the rest of the molecule. One of the common myths about polarity is that polarity or interactions between charges are limited to the bond. But that's not actually true. What is around an atom matters. So, for example, if we have a carbon with a positive charge, let me change the color here so you can see that better. If we have a carbon with a positive charge, this positive charge does not only affect that carbon, it affects everything around that carbon because positive charges have magnetism, they have magnetic fields. So what happens? In a polar bond of somewhat distant size, because the carbon-hydrogen bond is actually too small, but the carbon-carbon bond here has electrons in it. Those electrons are not immune to the positive charge that this carbon has. The electrons in the carbon-carbon bond, which is a nonpolar bond for intents purposes, are going to be attracted to the positive charge of a carbocation. So these electrons are here, and we show it by this arrow that we draw on the bond, are going to be drawn closer to that positive carbon. And this is going to happen anytime we have what we call an electron donating group, like the alkyl group. Alkyl, remember, and we have to remember this vocabulary that we use for chemistry. Alkyl group means carbon chain. Remember, alkyl means an alkane or an alkene or alkyne, carbon-based stuff. So carbon chains are referred to as alkyl groups. So this carbon chain right here, because this carbon-carbon bond is nonpolar, this carbon is not very electronegative to compete with a positive charge. The electrons in that bond are drawn towards the carbon with a positive charge. They're essentially polarized. But what happens? The more carbons we have attached to that carbon, the more that happens. In a secondary carbocation, there are two carbons which are going to have their bonds polarized towards a positive charge. In a tertiary carbocation, we're going to have three carbons polarized towards that positive charge. So the more carbons we have attached to the carbon with a positive charge, the more carbons we have in that carbocation attached to the positive carbon, the more electrons are drawn towards the positive carbon, because a bond is made out of two electrons. So in this primary carbocation, two electrons are drawn towards the positive charge. In a secondary carbocation, we have four electrons drawn towards that positive charge. In a tertiary carbocation, we have 6 electrons drawn towards that positive charge. But why does that matter? Why does it matter that these bonds are polarized? And what does that have to do with the stability of the carbocation? Stability is another way of saying non-reactive. So the more stable something is, the more non-reactive it is. Because when things react is when chemical reactions happen. When things interact, that's when chemical reactions happen. When we call something stable, we are calling it non-reactive because it does not easily react with other things. It is more likely to stay existing. So when we talk about a carbocation's stability, what we are talking about is how much does it resist reacting. And what is the main thing that causes things to react in chemistry? Charges. Charges attract electrons. Positive charges attract electrons. Negative charges repel electrons. So charges make things more reactive. So what happens here? Why is a tertiary carbocation more reactive? Or sorry, less reactive. Why is it more stable? The positive charge of a tertiary carbocation has 6 electrons, which are negative, counteracting the positive charge. Meaning the positive charge on a tertiary carbocation is less positive than the positive charge on a primary carbocation, which only has 2 electrons dampening that positive charge. So it only has 2 electrons kind of counteracting the positive charge. That makes that positive charge more positive. because the positive charge on a primary carbocation is more positive than the positive charge on a tertiary carbocation, which is less positive, the tertiary carbocation is more stable because it's not going to attract nucleophiles as easily. It's going to exist for longer. How does that relate to SN1 and SN2 mechanisms? The reason why tertiary halogenoalkanes can undergo SN1 mechanisms is because they create tertiary carbocations, which are more stable, whereas a primary halogenoalkane will create a primary carbocation, which is less stable because the charge on it is more positive. So because the stability increases from left to right, so will its likelihood of existing. Because as we go from primary to secondary to tertiary, they get more stable, they're more likely to be created, they're more likely to exist. Therefore, a tertiary halogenoalkane will create a tertiary carbocation, which is more stable, whereas a primary halogenoalkane can't make a primary carbocation. It's too unstable, and so it will instead opt to undergo SN2 mechanisms. So primary halogenoalkanes undergo SN2 mechanism because they're not going to make a carbocation in that way because primary carbocations are unstable, whereas a tertiary halogenoalkane will opt to undergo SN1 mechanism, which does create a carbocation. And that's okay because that tertiary carbocation created is more stable than our primary carbocation. And that's why tertiary halogenoalkanes undergo SN1 mechanisms, which create carbocations, and primary halogenoalkanes undergo SN2 mechanisms, which avoid the carbocation. That's it. That's the explanation behind the two different mechanisms for nucleophilic substitution reactions of halogenoalkanes. That is it for this section. I will see you all in the video for the last section of chapter 16, which will cover elimination reactions.